Okay, moving on to trigonometry. This is our longest unit, I would say. It's got 10 lessons in it. I guess we had another one with 10 lessons in it, but this one has quite a lot of information in it, and we need to move through it at a pretty quick pace. Lesson 2 is all about radian measure, and that's going to be all new stuff. Lesson 1, this is all review. So I'm going to move pretty quickly through this lesson, and if you need review, then you should do lots of the homework questions or the assignment questions for this one. But hopefully we can remember a bunch of what we did in grade 11 for this. There's a lot of definitions. This is basically going to be drawing our angles in 360 degrees in a full circle, and bigger than full circles actually. So we have rotational angles. A rotational angle is the angle that's formed from standard position being the positive x-axis, so the line that goes to the right. And if it's positive, it's rotating counterclockwise, and if it's negative, it's rotating clockwise. The initial arm is called the x-axis in standard position, and then this is called the terminal arm. Lots of definitions. Okay, let's try a couple questions. I've already got them filled in, but I think we probably understand this part at least. If you have to draw 290 degrees, so you would start at the positive 0 degrees, and then you'd start rotating. That's 90, 180, 270, 280, 290, so an extra 20 degrees pass straight down. And that's going to be quadrant 4. So hopefully you remember, we call quadrant 1 the best quadrant. It's the one where everything is positive if you have coordinates. So up here is quadrant 1, and then it goes counterclockwise 2, 3, 4, the same way the arm rotates. What about negative 135? Well, that's going to go negative 90 plus an extra negative 45. So it should be that 45-degree angle in quadrant 3. What about 750? You might need to pull out a calculator at this point. So you'd say, well, that's 360, one full circle. Another 360 would make 720, so a second full circle, and then there's 30 degrees left, and that ends up in quadrant 1. So just some easy drawing angles. Can we do that with some coordinates? This thing's not bending right. The point A lies on the terminal arm of a rotational angle theta. In each case, draw the angle theta in standard position. So what terminal angle would end up through the point negative 3, 4? Usually we consider these things rays, so they start at the origin and they go on forever when you rotate by an angle. So which one travels through negative 3, 4? So negative 3, positive 4, you draw an angle going through that. Negative 7, negative 2. So negative 7, negative 2, draw an angle traveling through that. Does that ask what theta is? No, it just says draw the angle. So we don't need to calculate theta this time. You would have to use your trig stuff to calculate that, but we could do that eventually. Draw the rotational angle in standard position. Okay. Anything new here? Rotating 150 degrees, easy. Rotating negative 210 degrees, easy. Rotating 510 degrees, easy. Oh, the one special thing about this is now we can start talking about coterminal angles. All of these ended up actually being the exact same terminal angle. All of these are the exact same line drawn, even though the rotational angle was different. All the terminal angles were the same. So we call this a coterminal angle, or coterminal angles. A coterminal angle is any angle which ends up with a, what do you call that, a rotational, a reference angle, which is the exact same, basically. The line ends up being the exact same. The principal angle of a set of coterminal angles is the smallest positive rotational angle. So we do have one, so even though these are all the same, there is one that we like to see more than the other ones, and you probably guessed it's this one right up here, the 150. That's what we call the principal angle. So principal angle reduces anything that's in weird numbers into a 0 to 360 degree calculation. That's what it says here. So the very first circle that we're doing, that's going to be the principal one of it. Just because that's the one we like to see a bit more. So that's 150 in this case. This is actually the really interesting part. I'm going to actually write this one out because I don't like using the I. There are infinitely many angles that are coterminal with any given angle. They can be found by adding or subtracting multiples of 360 degrees. The set of all coterminal angles can be described with the reference angle with reference to the principal angle as p plus 360 degrees n, where n is an integer. And this is going to be really important. I am going to expect this of you. This is a 30-1 new expectation. When we're looking for solutions sometimes to these things, it comes one of two ways. Sometimes we say, what are all the solutions within the range 0 to 360 degrees? In which case, all you have to do is find the principal angles, which make it true. Sometimes we don't say that. Sometimes we just say, what are all the solutions? What are all the, we could go back here for example, what are all the angles which travel through the point -3, 4? I don't know what that angle is, but let's pretend that's an angle. Let's pretend we found that solution was theta is, what does that look like? 120 degrees maybe? So let's say we found that one is 120 degrees, but we wanted to find every possible solution. So 120 degrees isn't actually every possible solution. You could add 360 to that. Which is 480. You could add 360 to that, add 360 to that. So the way we actually write all of them is we write our principal angle, 120, and then we say we add 360 times n. We always use n pretty much. And n can be any integer. So it could be 1, 2, 3, 4, 5. It could be -3, -7, -9. If we write this line, then we've written every single solution to that problem. And that's what we like to see. They use the capital I. If you want to use the I, it's actually a double-lined I. Both of these means integer. I see Z a lot more often though, so I always use Z. Okay, so I think that's the only new thing in this lesson. And we'll get to that eventually. I'm not really going to do a lot of that. Actually, here's an example with it right away though. Determine the angles between -360 and +360, which is coterminal with a given angle. And then write an expression that shows all angles. So 285. So this is from 0 to 360, so we would need the -1. So we need to subtract 360, and it's the same as -75. So that was A. We're not adding 360, as it says here, because that would be, our domain ends at 360 this time, but it goes backwards to -360. Now let's write all of them. So it's 285 plus 360 times n. Most people don't put the degrees there. N as a member of, I would use Z there, integers. That's fine. This one started at -13, so we need to add 360 this time to keep it in the domain, and it's also 347 degrees, in which case we always write it as the principal angle, 347 plus 360n, and is an integer. And same thing with the last one. Actually, this one is outside our domain entirely, so we have to do it twice. We have to subtract 360 to get the principal, and then subtract another 360 to get the -1, and then we can rewrite it with the principal in all possible solutions. So not too tricky. Reference angles. We made a big deal about this in grade 11, so I'm hoping you guys remember reference angles. Reference angles are the shortest distance back to the x-axis. And the importance of the reference angle is whenever you're doing your trig calculations, the only number that matters in the trig calculations is the reference angle. Where it is in the circle only changes the sign after that. The reference angle tells you what the number is, and what quadrant it is tells you what the sign is. So a reference angle is always the acute angle formed between the terminal angle and the x-axis. So it's always a small angle, the shortest angle you can. So in 120 degrees, we would actually call it this reference angle here, which is 60 degrees. Makes sense. In each case, sketch the rotational angle and state the reference angle. So what's 243 degrees? Well, it's past 180. It's somewhere down here, 243. So that part we probably can't do precise unless you pull out a protractor, but you can just guess for now. But now what's the reference angle? There are formulas for these, and we're going to get to them down here, but I never actually memorized the formulas when I was in school. If you're a good memorizer, maybe you want to memorize the formulas, but I always just visualized it. I said, if I traveled past this 180, then whatever this length is going to be what number I have, take away the 180. And that's what they did here. 243 minus 180 gives you a reference angle of 63 degrees. And we call that theta r. That's our theta symbol. That's an unknown angle, and r for reference. 337 degrees. So way around, somewhere over here. So this time, if I'm looking for this angle here, this time I actually want to take my 360 and take away whatever my theta was, which was 337. 360 minus 337 should give me what's in this little area, which is 23 degrees. Okay. Last one, 70 degrees is just 70 degrees. If it's in quadrant 1, it's great. We can just say what the angle is. Everything's just fine. And all the measurements are going to be positive. Sine, cosine, tan. So we really like quadrant 1. Okay, the diagram below shows you all the formulas for this. Some people memorize these. Like I said, I don't. If it's in quadrant 1, whatever the rotational angle is the same as the reference angle. So you don't have to do anything. In quadrant 2, you're going to take 180 degrees and you're going to take away whatever your angle was to get the reference angle. In quadrant 3, you do the opposite of that. It's 180 degrees, and you add, the rotational angle is 180 plus the reference angle. So you actually do your angle, subtract 180. So you actually flip the other two. Whatever your angle is, subtract. This is written not how I would write it. And then over here, this time you would take 360 and you would subtract your rotational angle. I would flip all these because you usually are solving for reference angle. But hopefully that makes sense. If you want to memorize, you can. And we only have one more part. Well, 2 more examples. I am going quite quick. If you ever want to pause, try some on your own. I don't think I need to say. I'm sure you guys are already doing that. It's really a question of whether you remember this stuff or you don't remember this stuff. And if you half remember this stuff, which I'm expecting, then it's mostly about the practice. You've got the examples here to go back to, but it's mostly going to be about just trying it. State the reference angle for each of the following rotational angles in standard position. So why don't we actually cover these up and actually show some calculations for once. If you had 195 degrees, well, what quadrant is that? That should be quadrant 3. So I always draw a little sketch. We're looking down here. So in that case, I want to do my 195 take away 180. So theta reference is going to be 15 degrees. That's it. Not too tricky. Negative 258, like it says above, we can't do much with that number because it's kind of confusing unless you actually draw it out perfectly. But we want that to be standard. So if we get that to standard position, what we have to do is add 360 degrees. Is that right? Yeah. Negative 258 plus 360 is 102 degrees. So that should be 90, 102, should be somewhere up here. So that time we're going to do our number, 180 subtract our number. Which is equal to 78. So this guy right here is our reference angle, and that's 78 degrees. Call that theta r. Okay, negative 810. So first thing we got to do is get into standard position. So negative 810 plus 360, still negative. Add another 360, still negative. Add another 360, and I get 270 degrees. And that's our principal angle, remember. Now we need our reference angle. So where is 270? 90, 180, 270. That's actually straight down. So what is our reference angle in this one? Well, it's the shortest distance to the x-axis. So it's not 0 degrees. Shortest distance, it's either way, but it's going to end up being 90 degrees. In that case. And that's kind of one of our special cases. The numbers turn out funny on that one. But yeah, that's what it should be. 90 degrees. Okay, last question. Determine 4 angles between 0 and 360 which have the exact same reference angle as negative 128. Well, first thing we want to do with negative 128 is turn it standard. And I get 232. So they actually found this one third, I think. 232, so this guy down here is actually the first one. Then you need to find its reference angle, which 232, they subtract 180, and you end up with 52 degrees, I believe. Yeah, 52 degrees. So I would have found that first, I would have found that second, and then you need to plug in the other ones. So this guy over here should be 180 subtract 52. And this guy over here should be 360 subtract 52. And that's what they did to find all 4 reference angles. So there's a whole bunch that are the same. That's the tricky part about trig. There's so many different answers. Usually in a solution, only 2 of these will be true, depending on the sign of what we gave you. So we would say, when is sine of theta equal to negative 3/4? In which case it's, you gotta use the cast rule, C-A-S-T, and then you have to say when is sine negative. So C-A-S-T, so it should be these 2 ones, quadrant 3 and 4, in which case it'd be these 2 solutions. Something like that, but we'll get into that. That comes up in the future. Not as quick as I thought this lesson would be, but okay, lots of practice on this one if you need it. And then I'm gonna make a second video, and the second one is all new stuff. We basically all the exact same rules. We just have to look at all with radian measure now. So we're going to be converting everything into radians, and that's the grade 12 thing. Everywhere, that's what you do in grade 12. And it's a bit hard at first. It takes practice.